We connect our discussion about photon energies with something we talked about when we talked about electromagnetic waves in the last unit, dealing with the electromagnetic spectrum. So again, photon energy, I've shown this equation 3 times now, it's very important. The energy of a photon is equal to Planck's constant times the frequency of that photon, or Planck's constant times the speed of light over the wavelength of that photon. So if you have the frequency, multiply by Planck's constant to get the energy. If you have the wavelength, take Planck's constant times the speed of light divided by the wavelength. Your book notes that Planck's constant times the speed of light is 1240 electron volts per nanometer. So if you use this in place of in the numerator here, and you have the wavelength in nanometers, the nanometers will cancel and give you the energy of the photon in electron volts. So it's a way of simplifying that part of the equation. Now, so at a specific frequency, I can calculate what the energy is of a photon, or at a specific wavelength, I can calculate the energy of the photon. And we talked about binding energy when we talked about the photoelectric effect. Atoms are composed of electrons bound to a positive nucleus, but if you give one of those electrons enough energy, you can liberate it. You can break that electron out of that atom or molecule. This is called ionizing. And if you had a chemistry class, you've learned about ions. Ions are basically charged atoms, right? Are charged molecules where they have an extra electron or they're more likely missing an electron. These ions are created, you can create them by, of course, bombarding atoms and molecules with light. And if you give it light of a specific frequency or wavelength, that the light is energetic enough to liberate an electron, you've ionized that molecule, you've ionized that atom. This can be bad. This is called ionizing radiation. Ionizing radiation is bad for biological substances like you and me, because those liberated electrons act as little cannonballs, break through the rest of the cells in your body that can break apart rather fragile molecules like DNA and RNA, causing mutations, causing cancers. So ionizing radiation occurs when photons are about 10 electron volts or higher. In this region, 10 electron volts and higher, photons can cause biological damage. So this usually corresponds to ultraviolet, X-ray, and gamma ray light. Visible light is usually not ionizing. Ultraviolet light is. That's one of the reasons you wear sunblock, is to prevent cancers, skin cancer, because of the ultraviolet light depositing on your skin, breaking up, ionizing atoms and molecules in your skin, those free electrons then going through and destroying rather fragile molecules in your cells. So this allows you to calculate the photon energy. Well, there are 7 ranges in the electromagnetic spectrum, different discoveries, each has a historical significance, but we now know that all different types of light are basically, it's the same phenomenon. It's an electromagnetic wave. The only difference is the frequency or wavelength of the wave. Different frequency, different wavelength gives you different energy. So radio photons are far less energetic because they have big wavelengths, low frequencies, compared to gamma ray photons, which are very highly energetic. So going down from decreasing energy, and I'll show an electromagnetic spectrum up here on the right, the one from your book or a similar one. The range of electromagnetic radiation goes from the long wavelength radio waves all the way to short wavelength high energy gamma rays. So the gamma ray is the highest energy. Below that, lower frequency, lower energy X-rays. Then ultraviolet light. All 3 of these are ionizing radiation. None of them are visible to the naked eye. There's a visible range of light that you and I can see. Most of us can see with our eyes. Below that, infrared, microwave, and radio. So there's 3 long wavelength ranges that we can't see, 3 shorter wavelength ranges that we cannot see. The shorter wavelength, high energy, this is ionizing radiation, it's dangerous radiation. Below, non-ionizing, can still cause some problems, but not as dangerous as the ionizing radiation. And your book goes through talking about the sources of these types of energies. Gamma rays we will learn typically come about through nuclear decay. So inside the atomic nucleus, when energy levels change, when a uranium nucleus, for instance, decays, it can release gamma radiation, very high energy radiation. X-rays we can produce using basically a photomultiplier tube. It's just a high voltage tube that causes electrons to crash into other atoms. When those electrons get knocked out in those atoms, outer shell electrons jump down, releasing X-rays. So we can create X-rays. This is how X-rays are created, for example, in medical fields when you take an X-ray. Ultraviolet radiation, there's atoms that create ultraviolet radiation. Very hot gas can create ultraviolet radiation. Visible light, high temperature objects can create visible light. Spectral changes, the lights overhead, the fluorescent lights, are transitions of atoms within, or electrons within an atom. They can release visible light. Infrared, microwave, and radio radiation, again, lower energy, they can create, this radiation can be created more easily. Infrared, you and I are producing infrared light right now, just our body temperatures. Creates a black body radiation, we're producing infrared light. Microwave radiation, again, oscillating electric field, can produce microwaves fairly easily. We have microwave ovens in most of our houses. Radio waves are passing through our bodies right now from large radio antennas, usually at higher altitudes. Cell phone radiation, so on. All of that is produced by basically oscillating electric fields. Taking charges and oscillating in an antenna, producing an oscillating electric field, which creates an oscillating magnetic field, which creates electromagnetic radiation. So these 7 ranges you should know, and the use of each of these, right? Obviously, what we use radio for is pretty obvious. What we use microwaves for is pretty obvious. Gamma radiation has a lot of medical uses. Gamma knife surgery, gamma rays, and radiation can destroy tissue, so it's used in radiation treatment for cancers. X-rays, obviously, use for medical diagnostics because X-rays can penetrate the soft tissue in our bodies. They don't penetrate the bones as well, giving us a contrast between the bones in our bodies and the soft tissues. So these are the 7 ranges for electromagnetic spectrum. Again, each of these has a different energy range, ranging from the high energy gamma rays to low energy radio waves.